All right, so today's lesson we are looking at topic 4, forces, loads, and stresses. All right, we're going to talk about two kinds of forces today. External forces, these are stresses that will act on a structure from the outside. And we'll also talk about internal forces. These are forces that act on an object from the inside. So internal forces, these are internal stresses, and they can change the shape or size of a structure. And if that happens, there can be deformation. Deformation is when there's a change in a structure when a force is acting on it. So if you see deformation, that's an indicator that the materials are stressed, and it can lead to either repairable damage or it can lead to the complete failure of a structure. So when designers and engineers are making structures, they need to have an understanding of both internal and external forces to prevent these damages and these deformations. So we'll talk about external forces first. So there's two categories. There's a dead load and there's a live load. So a dead load, this is a permanent force acting on a structure. So this includes the weight of the structure itself, and then gravity pulling down. So over time, the gravitational force, it can cause the structure to start to sag, to tilt, pull apart, because the ground beneath can either shift or compress under the load. A live load is a changing or non-permanent force acting on a structure. So things like wind, force of wind, the weight of things that are in or on a structure, so like people, furniture, like snow and rain on the roof, those would be live loads. They also include impact forces caused by objects colliding with the structure. So usually most structures are designed to withstand forces at least 2 or 3 times larger than their expected live load. But sometimes live loads can become extremely large for a short time, like if there's a storm or if there's a collision and the structure can be damaged. All right, so next we'll talk about internal forces. The 4 internal forces we're going to talk about are tension, compression, shear, and torsion. So tension force, if you look at the arrows here, it's pulling apart. So a tension force, it's like a stretch. So tension forces, they stretch a material by pulling its ends apart. So something that has tensile strength, that's going to measure the largest tension force the material can stand before it breaks. Compression force, so again, notice the arrows, they're coming together. So a compression force, it crushes a material by squeezing it together. So something that has compressive strength is going to measure the largest compression force the material can stand before it loses its shape or breaks apart into pieces. A shear force, sorry, one second. So the next one I was talking about was shear force. So notice the arrows in opposite directions. All right, so it's like a bend or tear. That's what a shear force is. So shear forces, they bend or tear a material by pressing different parts in opposite directions at the exact same time. So that's a shear force, kind of like tearing paper. That would be looking at that. Shear strength would measure the largest shear force the material can stand before ripping apart. And the last one is torsion. This is a twisting motion. So if you notice the arrows, they're showing like the twist in opposite directions. So torsion forces twist a material by turning the ends in opposite directions. So if a material has torsion strength, that's a measure of the largest torsion force the material can stand. It'll still spring back to its original shape. Bending force. A bending force is a combination of a push or compression and a pull or tension forces. It'll result in a temporary curving. a curving change in the shape of structures. So for example, if you have like a plastic ruler and the bending of a ruler, that would be a combination of both compression and tension. This is showing cross-country skiing. The cross-country skis, they're designed to bend when a force is applied. Right here in this area here, that bending, it allows the middle, called the camber, of the ski to contact more snow, and therefore giving the skier a better grip when pushing off. So that's an example, another example of the bending force. Here we're just looking at spider silk. It's the strongest material known. So these dragline fibers are spun by spiders when they make the frame of a web, and also when they're dropping from high places. And these fibers have they have high tensile strength, and they're very stretchy. So it takes a great deal of energy to break them. Strong enough to trap a bird. Measurements of dragline fibers have shown that they're 5 times stronger than an equal mass of steel. So even stronger than Kevlar, which is the material made in bulletproof vests. So if a strand of this spider silk were as thick as a pencil, it could stop a speeding 747 passenger jet. So right now, scientists are working on genetic engineering to develop a bacteria that can produce this spider silk. Okay, because it is very super strong. So next, we're just talking about resisting stress. So steel, it has high tensile strength. So if we look at the particles here of a steel, we can see that each metal particle, it attracts very strongly the other particles around it. The forces, they're directional, so the particles, they form a regular arrangement. So therefore, it has a very strong tension force. A very strong tension force will be needed to separate those particles and break the material, all right, because it has those strong forces pulling its particles together. This is graphite. So graphite particles, they attract strongly in some directions, but hardly at all in other directions. It has a low shear strength. It's a form of carbon, such as in a pencil, you have layers of graphite in a pencil lead, and then when you're writing, it rubs off, it leaves a mark on the paper when you write. Okay, so the particles are arranged in layers, but the forces between the layers are relatively weak. All right, so the layers, they slide over one another, therefore it's slippery. It does make a good dry lubricant. This example is rubber. So when we look at the particles, each rubber particle attracts many other particles in all directions. So rubber, it has high torsion strength. Okay, so torsion, again, that was that twisting motion. So each particle is attracted in all directions to the other particles around it. So the particles, they'll hold together even when it's twisted out of shape. So think of like rubber, like erasers and so on. They do have that high torsion strength. All right, so last is just a quick video on internal forces acting on structures. So I'll pause it here.